Hi, this is Naman Kumar Singh, 19BCE1025, and I'll be demonstrating frequency domain filtering. To start off, I'll be demonstrating the low pass filter, or we call it smoothing. And for the frequency transformation, I have used discrete cosine transformation. Now, to start with imports, I have imported CV2 to handle image functions, matplot library to in order to plot the image, NumPy to handle arrays. Now, first, we'll read the image here. Then we need to apply the discrete cosine transformation or convert into what we call as f of uv. Now before that, we need to typecast the input image to float 32 values. By default, it has integer type values, but for DCT function in CV2, for it to work, we need to have it in float 32 type. So we typecast it here and pass it to the DCT function. Now that we have our transformation, we need to center the impact. So we are performing the shift. It is equivalent to converging the image using -1 power x plus y that we do in Fourier frequency transformation. In the same way, we are doing it here. We are using the inbuilt library, and now we are getting the magnitude, original magnitude, by using 20 into log of a function. This gives us the as the intensity would have been in an original image. So now we are getting the rows and columns. Then we are getting center of the row and center of the column, or the center of the entire image, in order to produce the mask or create the or generate the mask having the radius this much. So now x comma y are all the points of the image. Now we are plotting the mask area to be x minus a naught whole square plus y minus b naught whole square is greater than or equal to r square. What it does is, whatever the values that lie outside this radius r will be turned to 0, and whatever the values are inside will be turned to 1 upon this value, because coming to the low pass filtering, the general convention for mask is to take the values such that they add up to 1, because whenever we multiply them with the intensity, what it does is it takes the average ultimately. So automatically we know that it will be 1 upon row into column. So anything outside this circle will be turned to 0, and anything inside will have this value. So now that we have got our f of uv over here, dct this, and now that we have got our h of uv, that is, this is mask. Now we need to multiply them to get our the image. Now to get the frequency intensity values, we use 20 into log of function. Now that we have applied both of these, we need to get back the original image. To get back the original image, again shift of origin takes place to get back to its original value. Now inverse discrete cosine transformation, IDC inbuilt function, is used. Now again getting back the magnitude and the code from here till last. What it does is it simply plots the image in matplot library. So this was our input image. Now we apply the DC to it to get this. Now this was DCT plus mask, and this is after smoothing. Now we could see the effect of increasing or decreasing the radius. Let's say we decrease it to 20, and naturally it will have a blurry kind of visual. So it varies according to radius. Now let's make it 80. It's somewhat clean now. It's somewhat clean now. Now moving on to high pass filter, which is also used for edge detection. Everything here is same except for the mask that we apply here. So to start off, we read the image, convert to DCT or f of uv, make the shift, take the magnitude, get the center, and take the radius. Now here the mask, how it differs is, earlier what we did is we took the magnitude of 1 upon row into column. Here we fill the entire area with np dot ones, the entire array having the dimension row into column with ones. Now after that, whatever the value that lies within this radius selected R60, whatever the values are within this radius is turned to 0. Here mask area is turned to 0. Now that we have got our h of uv and f of uv, we multiply them to get the image. Now we get the magnitude, perform the inverse, and everything remains the same. So we can see here the output. The edge detection here is clearly can be seen. These are the sources, and we can see it here. Thank you. That's all, and hope my explanation was clear enough.